Chapter 4 is orthogonality, and section 4.1 is orthogonality of vectors and subspaces. If we say a vector v and w are orthogonal, then v transpose w is equal to 0. Or if we use dot product, the dot product of v and w will be 0. And in that case, a Pythagoras theorem holds. So v norm square plus w norm square will be v plus w norm square. And we proved it before, and if you want to prove that, I told you that we start with a more complex term. If you see that, I think a right-hand side is more complex, so we start with a right-hand side, and by definition, the norm square will be a dot product of itself, so we write in this way, transpose and v plus w, and this will be v transpose and w transpose and v plus w, and v transpose v plus w transpose v, v transpose w, and w transpose w. But we know that this is 0 and this is 0. And so what we have is v norm square plus w norm square. So this is the end of the proof. If we consider the multiplication a times x, and a is m by n matrix, and then we can write this as this, and this will be so this is where we are considering null space, and so the x vector will be an element of the null space, and we can see that the null space will be orthogonal to a row space, because in this equation, the x vector is an element of null space. But if you see this equation, since a1 transpose x is equal to a2 transpose x, by definition of null space, and we have am transpose x will be a 0. So we can see that c1 times a1 transpose plus, this is a linear combination of row vectors, will be orthogonal to any vector in null space. So we can say any vector in a row space, because row space is defined as the set with all the linear combination of the rows, is orthogonal to any vector in the null space. In this case, we write this way. The space are orthogonal each other. So a row space is orthogonal to null space. That means if you select any vector from row space, and then if you select any vector from null space, and if you check the dot product of the two vectors, and that'll be 0, because they're in that case that'll be 0, and then in that case we say the spaces are orthogonal each other. Example 1, ax is equal to 0, and there's a non-trivial solution 1, 1, 1. And in this case, a row space basis will be 1 minus 2 1 and 1 0 minus 1. This is basis because this vector and these vectors are linearly independent, and the null space basis is 1 1 1 because we have 3 variables, but rank is 2. So the null space, the dimension of null space is equal to 1. I mean, that's the number of free variables. So, but we find the one vector, one non-trivial vector for this ax equal to 0 vector equation. And so the null space basis is 1 on 1. And so we know the basis and the span of beta row. The row space basis will be row space. This is row space, and span of beta null space. I mean, a beta null is a null space basis. It's so we can a basis for null space. So we can this is n of a. And using a transpose, we can write this equation, and the column space of A, the basis, a basis of column space will be 1 1 and minus 2 0, and the left null space basis will be empty set because we have only 2 variables, but rank is right now number 2, so the left null space dimension is 0. Row space and null space are orthogonal space, and left null space and column space, they're orthogonal each other. And if V and W are orthogonal subspaces in Rn, then dimension of V plus dimension of W is less than or equal to n. And well, how about this one? V intersection W will be only a 0 vector because they're orthogonal. So you have to be careful because you might say the intersection of V and W is empty set, but if they're orthogonal, because they are subspace, so it's vector space, and V and W must include a 0 vector. So if they're orthogonal, and the intersection of V and W will be this set, the set with only a zero vector. We can define orthogonal complement. So if we have a vector space, and V is a subspace of, for example, Rn, and we can define a V pub. You read this V perp. It's, yeah, the meaning is perpendicular, so you just call this a V perp. And V perp is an orthogonal complement is when you select any vector here, x vector, and x vector will be orthogonal to any vector in Y. So Y is in V. And also, I mean, all the vectors in Rn, and also which are orthogonal to any vector in V, and we can say this is orthogonal complement. For orthogonal complement, for example, if a dimension of V is equal to R, and then dimension of V perp will be n minus R, because Rn dimension is n, and right now a dimension of V is equal to R, then the V perp dimension will be n minus R. We know that row space is an orthogonal complement of null space, and also we can say orthogonal complement of row space is null space. And so the row space dimension is R, and the null space dimension is n minus R, and we add up, and this is n. Because row space and null space, it's both are subspace of Rn. And we also know that a column space, orthogonal complement of column space is left null space, and vice versa, null space. And the dimension of column space is R, and the dimension of left null space is m minus R, and so we add up, and then we get m. Because column space and left null space both are subspaces of Rm. So any vector in Rn we can decompose into x row plus x null. It's a decomposition of any vector into two components, and one component is in row space, and the other component is in null space. We'll write this diagram again, and this is row space, and this is null space, and this is column space. And if Ax equal to B has a solution, a B vector should be in a column space of A. We know that by definition of null space, any element, any vector in null space will go to a zero vector. So it's not this direction, and so the null space a vector will go to a zero vector, and we know that. And suppose AXR, I mean XR means that it's a vector in the row space, and this is B vector, and also assume that AXR a vector prime will be B vector, and in that case we can see that A times XR minus XR prime will be a zero vector. And so we know that by definition of null space, and XR vector minus XR prime will be in null space. But we know that X, in this example, this notation means that XR, and we assume that XR prime is in a row space. So CA transpose. But we know that row space and null space, they're orthogonal complement. So so this is a subspace. I mean, the row space is subspace, and so XR minus XR prime will be in row space. But we already know that row space and null space, they are orthogonal complement. So the intersection of null space and a row space, it's only a zero vector. So in this case, XR is equal to XR prime. So this means that if you find any solution from at row space in this equation, I mean AX equal to B, and you find that a row space solution called XR, and this will be unique. We proved that. So, well, you could add some null space solution to this particular solution, but the rows in the row space, the solution of this equation is unique. But in general, we know that the solution of this equation is always XR plus XN. And where XN is in a null space. So any vector in null space. When we talk about a particular solution will be could be XR, but it could be different. I mean, it could be adding some components of null space solution. So we cannot say a particular solution is always XR. Yeah, we'll talk about combining bases from subspaces. If dimension of V is equal to n, but we have n independent, linearly independent vectors in V, and then that vectors is a basis. I mean, no need to check span. whether the vectors span the vector space or not. We don't need to check, because in this case, we know the dimension already. So if we know the dimension already, and then we have n independent vectors, we don't need to check whether they are span the vector space or not. And also, vice versa. I mean, same is true. So if dimension of V is equal to n, and we know that a subset S spans V, in that case, S is a basis for V. I mean, in general, we when we have any subset in a vector space, we want to check whether this subset could be a basis of vector space, and we need to check two things. One is whether the vectors are linearly independent, and the other is whether the vectors could be a generator. I mean, whether the vectors span the vector space. But if we know the dimension of the vector space, in this case, we can check only just one, whether a span, and immediately it could be a basis. And if we just check that, and it's n, they're independent, and then we can say, just independent vectors could not be basis. I mean, because if we have n independent vectors, and then we just get rid of some vectors, and they're still linearly independent. So if we find n linearly independent vectors, it'll be a basis. In this equation, a matrix is n by n, and if n columns of A are independent, but we know that so A is n by n, and n columns will be an element. I mean, n column vector will be an element of our n, a vector space, but we find that they're linearly independent. So we know that they span Rn for sure, because they could be a basis, because we know the dimension, and we have n independent vectors, and obviously they're going to span the whole space. So the n columns will span the Rn. So obviously in that case, Ax equal to B is solvable, because we can put any vector in B position. So we are still thinking of this equation. If n columns span Rn, I mean n columns of A spans Rn, and they're independent, because we know that the n columns belong to Rn. But right now they are spanning, so we can say they are linearly independent. So the n columns right now are linearly independent. So we can say Ax equal to B has only one solution. Because we know that solution exists, but in general, the columns are linearly independent. We know that in general case, I mean, the columns are independent. In this equation, we have no solution, or just one solution, but we know that the solution exists. Because the n columns span Rn, so we know a solution exists, and so we can see that Ax is equal to b has only one solution. In this example, we're gonna decompose the x vector, which is 4, 3, into two components. One is a row space component, and the other is null space component, which is 2, 4, and 2, minus 1. And we know that 2, 4 is in row space, and 2, minus 1 is in null space. And example 4, S is a subspace of R9, and dimension of S is 6, and we know that a V vector space is orthogonal to S. And what is a possible dimension of V? We know that dimension of V plus dimension of S will be less than 9. But we know that this is 6, so we know the dimension of V could be 0 and 1, 2, and 3. And B, V is equal to S perp, and what is dimension of V? Because dimension of V is 9 minus dimension of S, so this will be equal to 3. And S is row space of A, and our smallest possible size of A. Well, in this case, we know the row space of A matrix has dimension 6 already, and also it's a subspace of R9. So in this case, we can see that A should be this shape, and the size will be 6 by 9. Well, it could be bigger, 7 by 9, if we have a dependent rows, but the question is smallest possible size, and the dimension should be 6, so we have at least 6 rows. So that's why the smallest possible size is 6 by 9. The D is S perp is null space of B. So we can say S is row space of B. In that case, smallest possible size of matrix B. S perp is null space of A, and we know that S is a row space of B, and it's the same question. This question is the same question as this, and S is row space of B, and we know that in this case, the smallest possible size of B, 6 by 9. And this is the end of section 4.1.